So we are talking about 3 essential facts, and our first fact is over any length input value interval, the average rate of change for a linear function is going to always be constant. No matter what it is, if it is a linear function, it's going to be constant, okay? What constant means is that you're going to get a numerical answer. You're going to have a numerical value. That's a number. It can't have it won't have an X, a variable, just numerical. Okay. All right. Given consecutive equal length input values intervals, the average rate of change of any quadratic can be given by a linear function, which means that it's given in the format of mx plus b. As you go further into math, the m becomes an a because you're not necessarily talking about a specific linear equation. You're talking about a rate of a quadratic function or a function in general. So if you ever looked on the TI-84, you'll notice that it doesn't say mx plus b. It says ax plus b. Okay, lastly, the average rate of change over the closed interval of a to b is the slope of the secant line. The key thing here is that I'm giving you an interval. It's a closed interval. I'm saying from here to here with these defined values, you're finding the change. Okay, yes. Red basket up there still. Top and bottom. All right. So here we're going to talk about the average rate of change and concavity. Okay. So in the quadratic function, we can determine curvature or concavity of a graph by considering the average rate of change over equal length x intervals. Okay. So we're going to sketch secant lines on the graph shown below. So remember, the goal of a secant line is to get as close to the curve, but without actually being completely on it. Does that make sense? So our secant line, you don't want to be, harassing it. So I'm going to just like, oh, excuse me, let me get by. Okay. Okay. And again, oh, excuse me, let me get by. I didn't even touch you this time. I should have, but I didn't. Well, you know what I meant? The line, guys, the line. Y'all are childish. You're laughing. I didn't even laugh. You did. There we go. All right. There we go. Better. Okay. So notice that each slope is increasing and getting steeper when I'm coming off a curve, right? That's because when you're concaved up, you're going from a decreasing to a increase. That's what makes it a concave up, positive concavity right there, right? All right. When we're concave down, what's going to happen here to our slopes? They are decreasing. And that's because we're concave down. So we're going from an increase to a decrease. The slope is overall decreasing. They're in the red basket. You just open, hook. Okay.
What you doing if I find it?
She literally said the bottom last week.
To be fair, she did say
Yeah, but they kind of like look the exact same. Just like
Yes, it just barely, well, no, tangent is going to touch it. Secant line touches it and tangent's going to touch it, but the tangent is going to be like not as much. It's weird. Because your tangent, I'm describing that terrible wrong. Your secant line is going to go through 2 points, so it's okay if I have a secant line that goes through another point. Okay, a tangent, it will only go through 1 point at a time. But here we're only analyzing the curves, and I still think I was supposed to write the word secant there. I'm sure it's tangent lines.
Oh my goodness.
I will double check my life, but I'm pretty sure I should wrote tangent there. Bear with me. First year doing this. There we go. Yeah. We all are, you get to be the guinea pigs. I know, here we go. Pretty sure that I probably should have wrote tangent here. And I wrote secant. These are tangent lines, not secant lines. Yeah, there we go. Thank you. One word.
I don't care.
Yes. These are tangent lines. So a secant line would be, let me do it in a different color for you. So your secant line would be saying, I'm going from, okay, that didn't even go to, that didn't make it. That secant, it did not make it. It did not make it. The goal was to get to the other point.
Yeah, man. Oh, what a straight line.
There we go.
Oh, yeah.
There's my secant.
I thought.
It made it.
Yeah,
Yeah, you see what it is. There's a reason why I'm not an art teacher. Okay. We didn't need to agree. Okay, we could just keep going. Yeah, sorry, tangent. All right. So here, graphing the average rate of change across the quadratic function. So when we are going to use the function from example number 2, that f of x equals, I'm gonna write it really quick. So we're using f of x equals x squared minus 6x plus 5. Do we see that from example number 2? And we're going to use it to help us kind of analyze and talk about these parts. All right. The parabola is concaved up. How can I tell off the bat that this parabola is concaved up?
Wait, what?
Because it's a positive x squared, right? My leading coefficient is positive. So right off the bat, just looking at the function, I know that my leading coefficient is positive, and that's what makes me a happy parabola, right? Okay. All right, so because the average rate of change on the equal length interval is going to be increasing. I was like, oh, I thought I drew a parabola, but is my parabola? Interval is increasing by a factor of, and that's what we're going to talk about. How is it increasing? Well, we already did it. What did we say on example 2? How is it increasing? By 2, right? So on our thing, we said that our values were increasing by 2. We added 2 to each one of our numbers on our parabola, right? To go from one y to the next. Okay, we're going to let this be the slope of a new equation. Okay, now we also observe that the quadratic function changes from decreasing to increasing. When that change occurs, that happens at the vertex. The change from increasing to decreasing happens at the vertex. Okay, the vertex of this, let's go look at the graph. What was the